To semester 3, where we will be studying circuit analysis and design part 2. In today's lecture we will be discussing about RLC circuits connected either in series or in parallel. So let's have a look on a series RLC circuit where we assume that I of t is the current flowing through the loop RLC. The RLC circuit may be composed of two parts: the shaded part on the left containing Thevenin voltage source and Thevenin resistor. This Thevenin voltage source and Thevenin resistor might have come from a different combination of resistors and voltages in any other configuration. The non-shaded part consists of inductor and capacitor in series. We call voltage across the point at which the shaded and non-shaded parts are connected together, this point, as V of t. Similarly, we call voltage across resistor as VR. We call voltage across inductor as VL. We call voltage across capacitor as VC, whereas the source voltage is V Thevenin. Now we apply Kirchhoff voltage law on the left hand side, which is consisting of a shaded part, and this equation may be written as plus VR plus V of t minus V Thevenin equal to 0, and which may be reduced to the form V of t plus VR equal to V Thevenin. Similarly, the Kirchhoff voltage law on the right hand side, that is the non-shaded part, may be written as V of t equal to VL plus VC. When these two equations are combined together, that is, we can plug V of t in the equation on the left hand side, and hence we get the final equation as consisting of VL plus VC plus VR equal to V Thevenin. In order to characterize the response of series RLC circuit, we formulate the equations either in terms of VC of t or in terms of I of t. First, we adopt an approach where we formulate equations in terms of VC of t. We know that the final equation for series RLC circuit was VL plus VC plus VR equal to V Thevenin. We can replace the value of VR equal to IR according to Ohm's law, that is. Similarly, we must recall the famous relation in between current and voltage for inductor is VL is equal to LdI over dt and I of t equal to C dV over dt. Now, since I is same in series RLC circuit, we can replace this value of I of t equal to C dV over dt into this equation, and hence we get this equation, that is VL plus VC plus RT, and then I of t is replaced as C dV over dt equal to V Thevenin. Moreover, I of t can be replaced in equation of VL as equal, and this in this way equation of VL will become equal to L d over dt times C dV over dt, and hence we get VL equal to L C d square over dt square. Plugging this VL equation into this equation, we get a final equation for series RLC circuit as LC d square V plus RTC dV over dt plus VC equal to V Thevenin. In order to solve this equation, we need VC of 0 and we need dVC over dt at t equal to 0. These are called the initial conditions. Now, assuming that capacitor was charged initially to voltage V0 and inductor had current initially I0, we can have VC of 0 as V0, and similarly dVC over dt as governed by this equation is equal to I of t over C, and hence we get the initial conditions as Vc of 0 equal to V0 and dVc over dt of 0 equal to IC I0 over C, which is I0 over C. In an alternate approach, we want to write equations in terms of I of t. So in equation VL plus VC plus RTI equal to V Thevenin, we want to replace values of VL and VC in terms of I of t. Writing VL in terms of I of t is pretty straightforward by following this relation. VL is equal to LdI over dt. However, for VC, we would use the capacitor relation I is equal to C dV over dt, divide both sides by C and then integrate so that we can get a relation VC equal to 1 over C integral of I of x dx plus VC of 0. Now plugging the value of Vc and Vl into this equation, we get a final relation as LdI over dt plus 1 over Ci of x dx plus Vc of 0 plus Rti equal to V Thevenin. This is called an integral differential equation of second order because the first order one order is taken for because of this derivative and one order is taken because of this integral. As far as the initial conditions are concerned, we need I of 0 and Vc of 0. Now, since the capacitor is charged to voltage V0 and inductor is assumed to be having current I0 initially, so we have the initial conditions Vc of 0 equal to V0 and I of 0 equal to I0. Once equation for series RLC circuit are formulated, we consider the input voltage V Thevenin equal to 0 called the zero input voltage and observe the response of the circuit. The non-zero response of the circuit is observed when the input voltage is set equal to 0 due to the presence of storage elements, inductor and capacitor, which had some energy stored initially. As previously obtained, the differential equation written in terms of Vc of t is this one, and the integral differential equation written in terms of I of t is this one. In this equation, when we set Vt equal to 0, we get this equation. Similarly, in this equation, by setting Vt equal to 0 and also differentiating both sides with respect to t, then multiplying with each side with c, we get a differential equation of this type. The equation obtained when input voltage is set to be equal to 0 in both of these approaches appear to be similar in format. The only difference is that here the dependent variable is Vc of t and here the dependent variable is I of t. Therefore, if we learn the way how to solve this equation, similar approach can be adopted to solve this equation as well.